Okay, hi. So I will continue to talk about the propagator today in our explanation of quantum field theory. Uh, as, as you have probably remember, we cover the first order in the perturbation expansion of S, the S matrix, and which will give us a transition amplitude. And we established the correspondence between your interaction Lagrangian and the vertex. And today, the focus will be propagator, and it will emerge from our discussion of the evolution operator to the second order. Okay, so now let me remind you, this is the equation for the evolution operator U, and if we expand this U to the second order, then to the left hand side, U will becomes the second order of U, U2. And on the right hand side, just as in the leading order expansion, Hi is of the first order of the coupling constant lambda or G. Okay, therefore U will be the first order expansion of the evolution operator U1. However, U1 we already have solved it already, which we have the expression is the integration of the interaction Hamiltonian Hi integrated from T0 to T. Therefore, we have everything ready on the right hand side, and therefore we can solve the U2 by integrating the right hand side from T0 to T. Okay, and we set the we change the upper limit T into T double prime, and this T into T double prime, and integrate over T double prime. And this is the result of the second order expansion of the evolution operator. Therefore, this expression is very interesting. The first, it consists of two identical interaction Hamiltonian Hi. However, there are two integration. That means the T prime and T double prime needs to vary between T0 to T double prime and T0 to T respectively. Okay, and if you simply observe this expression, you can see that T double prime is always larger than, it's the upper limit of T integration. Therefore, T double prime must be always larger than T prime. Therefore, we can put it another way. This Hamiltonian at the left hand side is always later than the Hamiltonian on the right hand to the right of it. Okay, therefore it is a very indication that when we give you the final expression Hamiltonian, the first Hamiltonian must be later than the second Hamiltonian. Okay, so let me put that idea explicitly mathematically. The idea is that when I can write the expression here as this, put Hi T double prime into the integration. Therefore, it is Hi T double prime, Hi T prime doing the integration over this. And if you draw a diagram of T prime and T double prime, that's the two integration variable. The range, remember, T prime would be from T0 to T double prime. Okay, that means T prime must be smaller than T double prime. On the T prime, T double prime plane, it corresponds to this upper triangle. You can figure it out yourself from the expression. The purple red area is the integration area of this expression. On the other hand, this t prime and t double prime are just dummy variables. That means we can rename them. For example, I can define a new t prime as t double prime and a new t double prime as t prime. Therefore, this expression becomes t double prime. This becomes a t prime. Okay, so I just changed the notation. But they must be, but as I say, they are dummy variables. So it doesn't matter if I change the notation. And it will give you exactly the same result. That means this term is exactly equal to this term. Therefore, I can add them up and divide it by 2. It will be equal to our original expression. Okay, but now the magic is, if you write in this way, let us first focus on the integration range. I already told you that the integration range of the first term is the upper triangle. However, because t double prime must be larger than t prime, as it is clear from this expression. However, on the second expression, the integration range, let's forget about the integrand first. If you look at the integration range, t prime, it ranges from t0 to t prime. That means t prime must be larger, always larger than t double prime. T prime must be always larger than t double prime. Therefore, this integration range as illustrated on this t prime, t double prime plane will be the lower triangle here, the one with the white color. Therefore, I hope I convinced you that in regard to with no regard to the integrand, the two expression has the first term has the integration range on the upper triangle. The second term has the integration range of the lower triangle. So if you add them up, it becomes a square. It becomes a square. However, the two integrand are not the same. This is t hi t double prime ht prime, and this on the second term we exchanged order to give you hit prime and hit double prime. However, it illustrates that the first Hamiltonian has a larger time, meaning later time, than the time of the second Hamiltonian. So if I could possibly write an expression as this, hit prime t double prime times hit prime, but always set the earlier hi placed left, then I can combine the two expressions into one expression. But now the integration range will occupy the whole square. Okay, so the whole square means the t prime will be t0 to t. T prime will be t0 to t. And t double prime will be t0 to t. So t0 to t, it becomes a square if this kind of expression is possible. In this expression, I always place the earlier hi to the left and I put it wrong. In the later hi to the left. Later, I think I'm right. Let me check. Later, yeah, t prime larger than t prime, t double prime larger than t prime. So that means this one is later, right? Okay, so let me change the expression right away. Let's be later. Okay, so if I always put the later hi to the left and the earlier hi to the right, then I can put I can combine the two expressions to form this expression. And let me review again, at the higher triangle, t prime is t double prime is larger than t prime. So you got this expression as your integrand. However, if in the lower triangle, this one t prime will be larger than t double prime. So you need to replace, you need to switch the order of the two Hamiltonian, and this term will become this, exactly what I need. Okay, the point is the two areas or two ranges are exclusive. You either at the higher triangle or you had the lower triangle. So there is no confusion with this expression or this notation. Okay, so we succeeded at least formally combine the two expressions into this one. The only difference between this and our starting point is now we have a integration area as a square. You will see that a square integration area is very, very good for our expression. Okay. Now, so now I have this expression. Now again, let me remind you the ranges of the integration is a whole square, as I illustrated in this diagram. And in the integrand, the later, I'll change it later, correct it later. Okay, the later hi always placed left. And it is easier to express this kind of manipulation in terms of a theta function. Remember, you probably met this theta function in quantum mechanics, which is the function we use to when t1 is larger than t2, theta is equal to 1. If t1 is equal to minus t2, then this is equal to 0. Therefore, this theta function is to enforce the t1 to enforce that the t1 is later than t2. Okay, so with this theta expression, I can define a so-called time order product of A and B. And A and B corresponds to an operator with respect to time t1 and time t2. And it's easy to say, to define what it is. The time order just as defined, time ordered. Okay, I always put the later operator to the left and the earlier operator to the right. Okay, so please check yourself, this is correct. Okay, so with this t notation is exactly, I write it here in terms of words. Okay, so with this notation, I don't need this description, and I can write this expression directly as the time order of hi t double prime and hi t prime. Okay, so good. So we finally arrive at a very concise expression for the second order expansion of the evolution operator. Okay, and now with this expression, I can simplify it further by replacing this hi by the integration over space of the Hamiltonian density. And I have already shown you that the interaction Hamiltonian density is the minus of the Lagrangian interaction Lagrangian density. Okay, so I can write the h int as the Lagrangian int integrated over the space. Then put this back into here. Then this integration will combine. For example, the integration here will combine with this to give you d for x1. And the integration over space here will combine with the integration over time to give you dx2. So I can replace the t prime by t prime by t1 and t double prime by t2. And then this expression could be expressed as the time order of Lix1 times Lix2 integrated over x1 and x2. Finally, here the integration for space is from minus infinity and infinity. However, the time integration is from t0 to t. So it is still not Lorenz invariant. However, remember what we are interested in is not u, but s. S is u taken to the limit of minus infinity to infinity. That means this t0 will be given to minus infinity and t will be replaced by infinity. And then therefore all the four integration over space-time are from minus infinity to plus infinity. This integration, of course, is Lorenz invariant. Okay, therefore, and if the Li, the Lagrangian density are also Lorenz invariant, then we expect this whole expression are Lorenz invariant if this time order is Lorenz invariant. Okay, so you probably need to convince yourself the second point, whether time ordering is Lorenz invariant. Indeed, it is, even though there's a time in the definition. Usually, if you have a time in your definition, it usually breaks the Lorenz invariance. However, it is not the case here. Why? Because here it is a time order of two operators at two space-time points, x1 and x2. So imagine that x1 and x2 is the difference between them, the separation between them is time-like. Time-like, that means you can find a Lorenz frame. In that frame, the x1 is earlier than x2, or x2 is earlier than x1. So that's why it's called time-like, because the separation is time. So, but it's a very, very important property of Lorenz transformation that if x1 minus x2 is time-like, the Lorenz transformation cannot change the time order. It could change the time, the value of time difference, but it could not change the time order. Otherwise, it will break the causality, okay? And it could be checked explicitly that Lorenz transformation does not change time order. Therefore, if x1 minus x2 is time-like, then this time order is fixed. If x1 minus x2 is space-like, then the Lorenz transformation can change the time order. However, if x1 minus x2 is space-like, that means you can find a frame, a reference frame in which x1 is separated to x2 by space, and they happen at the same time. If the two things happen at the same time, they must commute with each other because they cannot relate it to each other. Okay, otherwise you will have a communication or signal transmitted in the speed of infinity. Okay, therefore it's a classic condition. If x1, x2 is space-like, then the operator corresponding to them commute. So Li x1 commute with Li x2. Therefore, the time ordering doesn't matter at all. So even though you can find the time sequence between T1 and T2 will depend on the Lorenz frame. However, the ordering does not matter at all because they commute with each other. Okay, therefore, this time order product is the Lorenz invariant. Okay, so we conclude that the whole expression is Lorenz invariant. Okay, therefore, as long as you choose let me put it another way, as long as you choose a Lagrangian density L as Lorenz invariant, then the S matrix is Lorenz invariant. Perfect. Okay, so that's the key idea of this of this whole thing. Okay, so we are done with the S matrix to the second order. And actually this with the notation of time ordering product. And actually this time order product, this notation is so powerful. All the evolution operator to the nth order could be written directly in terms of this time order. Okay, you just need to take an analogy from this, the second order expansion of U, to the nth order expansion of U, and it becomes this. Okay, and therefore the U with this nth order expansion, then you can put the expression to all orders, add them up together into a series, and you come up with a complete solution of the evolution operator. And this expression could be easily transformed into an expression of exponential function. Okay, because it is easy to see that if you take the take the time order out, then put this integration inside the time ordering, it is easy to see that this whole thing is the integration of hi from t0 to t to the nth power. Okay, and this expression is simply the exponential function of this time integration of Hamiltonian. And finally, after you evaluate the whole thing, then you take a time ordering. Then you got the U in evolution operator. Okay, so it is this expression. But I haven't proved it yet. And let me first mention that this solution was first given by Freeman Dyson, another hero of the QED, in 1923. And the proof is so simple. I don't want to ruin your fun and joy to see the proof. The proof is only one sentence, just one paragraph here. Okay, so you can check by yourself. The 3.23 is what I have here, and Tong used a very simple sentence to prove it in just one paragraph. Okay, I encourage you to read it, and you will see how simple it is. Okay, as long as you come up with the right expression, then it is easy to prove. Okay, finally, so now we have an expression of U. So again, if you extend the two sides of the integration to from minus infinity to plus infinity, then you got S matrix. That's a formal expression, but we can use this formal expression to derive the S matrix and transition amplitude. Now let me illustrate how we use the second order expansion of S, or second order expansion of U to calculate the amplitude for scattering. For example, AA scattering to BB. Of course, I'm working in the ABC model. You can see from the Lagrangian density, I have G, A, B, C. This is the interaction Lagrangian density. Then interaction Lagrangian density at another point x2. Okay, so if you want to calculate this amplitude, what I'm going to calculate is S, sandwich between AA and BB. And I designate the momentum of A as P1. Oh, sorry, this is P2. This should have been EP2. Okay. And P3 and P4. And according to this formula, S2 is equal to the integration, space-time integration of Lix1 and Lix2 time ordered. So I simply plug in this expression, space-time integration, Lagrangian density, and time ordered. But from here, you can easily see that in order for this whole thing to have a non-zero, and remember that all this A and B and C consists of the annihilation operator and creation operator, just as I have shown you last week in our discussion of vertex. Okay, there I told you that A and B and C actually consist of A plus A dagger, B dagger. Okay, I'm going to take all the calculation from earlier discussion to this expression here. So in order for the transition amplitude to be non-vanish, I need an A from annihilation operator from this A operator to annihilate this. So, and after the annihilation, I get an exponential minus I x1, x2, p1, x2. And so this is annihilated. But we have another A existing here, so I need this A at space-time x1 to annihilate it. After annihilation, I get an expression of minus I p2 x1, the plane wave. And okay, so now the A operator and the A state cancel each other, kind of. And we have B state, 2B particle at the outgoing state, so we need the creation operator of 2B field from our expression to create these two particles. So for example, I can have this x1b to create this particle, and then it gives you this expression, and we use this b to create this particle and then get the expression of this. Okay, sorry, there is a little bit not true, not correct. So that's almost the end. Now I have a vacuum here, I have a vacuum here, and the rest are numerical expression. However, we still have two operators. These two operators are the C operator. Okay, so if I put everything together, I put what's remaining into an expression. First, I collect all the plane wave solution and arrive at this. And then the two space-time integration, I collect it in front. And then there is a vacuum, and a C, at different space-time point, x1 and x2. But they need to be time ordered. Oh, I missed the 2g squared, so there should be a g squared here in front. Okay, so that's the expression we finally arrived. What we finally arrived is this expression, the C and C time order product sandwich between 0, the vacuum, and another 0, another vacuum. Okay, so this expression I finally arrived at, we call it the propagator between x1 and x2. Okay, so and it is not hard to see that this x1 integration give you a Fourier transform, x2 integration give you another Fourier transform of this x1 and x2. Okay, or put in another way, we got a P1 minus P3. P1 minus P3 pouring into this X2, and P2 and P4 pouring into X1. Okay, so why do we call it propagator? Because is there anything propagating? Yes, indeed it does. Because as I told you, this is C consists of a creation operator and annihilation operator, and let's assume first T1 is larger than T2. That means T1 is later than T2, and therefore according to this time order product, this will be written as this. Okay, and this C consists of a creation operator and an annihilation operator. Roughly, I can say it happening at x1. And this C, x2, is also a combination of A and A dagger, I should say C and C dagger. Okay, so but anyway, it's a creation operator of C and annihilation operator of C happening at x2. So after you expand this product, you got 4 terms, and only one term will survive, which is the creation operator create a particle at x2 and then annihilate it at x1, right? Create an operator, a particle C at x2 and annihilate it at x1. So put it into a diagram. We will have a C operator with a C particle created roughly at x2 and propagating to x1 and be annihilated there. And remember this, in the earlier expression, we also, let me show you the full expression. In the earlier expression, I also annihilate an A particle at x1 and create an B particle at x1. So I could also put in the diagram like this. At x2, I annihilate an A and create a B. And in x1, I also annihilate an A and create a B. And please check my momentum designation are correct, corresponding correctly with our earlier expression. Okay, so it's fun. It's hard to do it on the blackboard, even harder for online lecturing. However, it is easy for you to do it at home. Okay, so please check this diagram corresponds correctly with this expression. Okay, but this is for T1 not later than T2. What you may ask, what about if T2 is later than T1? If T2 is later than T1, then this time order should be written as CX2, CX1. And therefore, the combination in front at the left is x2, at right is x1. So when you create a particle, you create it at x1 and annihilate it at x2. So if you use the same idea to draw diagrams, you create a particle at x1 and annihilate a particle at x2. And the difference from the earlier diagram is easy to see. Why? That's because now the T2 is later than T1. If the T2 is later than T1, then the particle could only propagate to the future. You cannot propagate to the past. Okay, so that's why if T2 is larger than T1, then this C particle is created at x1 and annihilated at x2. If you compare to the first diagram, when T1 is later than T2, then the particle C must be created at x2 because it's earlier and annihilated at x1 because it's later. Okay, so that means in this expression, I actually combine the two diagrams. Remember, in this expression, x1 and x2 has to be integrated over the whole range. So there are a whole areas. T1 is later than T2, and also another whole range T2 is later than T1. Okay, so therefore these two integration range or integration areas are exclusive. Okay, so on the one you get the first diagram, but on the other you get the second diagram. So they do not contradict with each other. However, in this expression, you ensure the causality of the process. Okay, so I say that it is actually the sum of two possible but exclusive processes. Okay, and because the vertex are integrated over the whole space-time, that means the interaction could happen anywhere, anytime. and amplitude needs to be added up. So that's why we have an integration here. Okay, so but this integration, if you put it into context, you see that it becomes a Fourier transform of this propagator or precision time propagator. Okay, so so yeah, so that's why this is called propagator, because it designates a process for the particle to move from a space-time to the next, to another. Okay. Okay, so I suppose our next topic will take us a bit long time. So therefore, how about I stop here? And next week, I'm going to continue to tell you how we are going to calculate this propagator. The t order phi sandwich between 0 and 0. And this will become the key components of Feynman diagram and Feynman rule. Okay. Okay, so I cut this lecture notes, the lecture online lecture a bit shorter because I need a hospital visit today. But next week I will continue to talk about the propagator, and you will see how beautiful this whole project, this whole construct are. Okay, so see you next week.